Good morning, everyone. This is the second lecture of Chapter 8. So, as you know that we have been discussing about friction, dry friction, and what is friction, why do we have friction, all those things. So if you just a quick recap, what we did last time was whenever there are two materials in contact, two bodies made of different materials are in contact, and we are trying to move one body with respect to the other body, and they are in contact, so there will be some friction between those two surfaces, right? Even when you rub your palm of your hands against each other, there is some friction. You are moving a box on a flat surface, on a table, or on the ground, there is some friction. You use friction to stop the car, stop your bike, right? So in your brake system, you use friction. So all these systems use friction, and it's a very important concept of mechanics. Okay, so we discussed about friction. So today we are going to go over the practice problems in your handout. So if you see your handout, you have 3 problems. So let's start from problem 1. So let's see what you have in problem 1. So let's start with problem 1. Let's see what do you have. Okay, so if I go through the statement, the mine car and its contents have a total mass of 6 megagrams and a center of gravity at capital G. If the coefficient of static friction between the wheels and the tracks is 0.4 when the wheels are locked, find the normal force acting on the front wheels at B and the rear wheels at A when the brakes at both A and B are locked. Also, we need to find if the car moves or not, right? So there's a mine car with some weight, some mass, with some center of gravity, and there's some static friction between the wheels and the floor. So that's given. So we need to find the normal force acting on the front wheels at A and B, right? So this is what we need to find. Now, how do we go about this problem? We know that there's a friction problem because we have the coefficient of friction, and there is some friction between the wheels because the wheels are locked. So once we have a force P applied to pull the van, to pull this mine car, then there will be some friction between these wheels and the surface. We can call a road surface or any surface. Okay, so first of all, first thing, what we need is a free body diagram, right? So let's draw a free body diagram of the system which is given, right? I'm just going to draw this rectangle showing this mine car. So not a fancy one, just a rectangle. And here are these wheels. These are the wheels of this mine car, and this is the surface, maybe a road or maybe any surface on which this mine car is moving. Okay, so this is our mine car, and now I'm going to use some other color to show the forces. Okay, so first of all, this is the center of gravity of this mine car, and we know that what is acting at this center of gravity is the weight, right? Now, what is the weight? Weight is mass times gravity. We have the mass, which is 6 megagrams, so it will be 6,000 kilogram times 9.81 meter per second square. So we get around 58.86 kilonewtons. Okay, so this is your weight of this mine car, which is acting at this point G, which is the center of gravity of this mine car. Okay, then we have this guy, the force P, which is 10 kilonewtons. force with which this minecart is being pulled towards negative x direction, right? Okay. Now these are the two forces. Now let's talk about these wheels. So we know that there's some normal force, right? This is point B, this is point A. So we have two normal forces, let's say N sub A and N sub B, right? Then as the minecart is moving, or the force is applied to move this minecart in the negative x direction, so the friction force will be in positive x direction, right? Opposite to the applied force. So here is this guy and this guy. This is F sub A, this is F sub B. The friction force at A and friction force at B. Okay. Now we have some dimensions given. Let's put those dimensions. So let's see, this is 1.05 meters. This is 0.6 meters. This is 0.9 meters. That's about it. This is all the data which is given. So now we are done with the free body diagram, showing all the forces, the applied force, the weight of the minecart, and then the friction forces and the normal forces at point A and B. So these are all the forces. Now, how many unknowns do we have? So we have FA, FB, NA, and NB. So we have four unknowns. So four unknowns. We have four unknowns, right? Okay. Now, next step, we need to apply equations of equilibrium. Equations of equilibrium. So let's take moments at point B. It's point B. So it's counterclockwise positive. The sign convention, summation of moments at point B equals to 0. Okay. So if we take that, we have NA times 1.5 is the moment arm, and we have 10 kilonewtons force times 1.05 is the moment arm. Okay, then we have the moment from the weight, which is 58.86 kilonewtons times 0.6, which is the moment arm, equals to 0. So these three forces are creating moments at point B, right? Okay. FA and FB are not creating moment because they are passing through point B, right? We have shown them just for convenience at this place, but in fact they are acting at this point, right? So they are passing through point B, both FA and FB, so they are not creating any moment. And B is also passing through point B, so that is also not creating any moment. Okay, so now we have this equation, and from here we can just simplify and find the value of N sub A, which is 16.5 kilonewtons. Okay, so we are done with one unknown. Now let's apply some other equation of equilibrium. Let's apply upward positive sign convention, summation of forces in y directions equals to 0. Okay. So if we do that, how many forces do we have in y direction? We have the weight of the car, we have N sub A, and we have N sub B, right? So we already have N sub B, which is N sub A, which is 16.5 kilonewtons, plus N sub B, which is unknown, and the weight, which is acting downwards, so it's a negative 15.86 kilonewtons, equals to 0. And from here we get N sub B, which is 42.3 kilonewtons. Okay, so Now we are done with two unknowns, n sub a and n sub b. Now we want to find fa and fb, right? So that's why we need to apply friction equation. So apply friction equations. The third step, apply friction equations. Okay, we know what is friction equation. F equals mu s times n. N is the normal force. Mu s is the coefficient of static friction. Okay, so let's apply at point A. So where you get Fa equals mu s times Na. Okay, mu s is 0.4 and Na is 16.5 kilonewtons. So we get 6.6 kilonewtons as your F sub A, the friction force at point A. Okay. Similarly, if you apply the friction equation at point B, we get Fb equals mu s times Nb. Okay, so 0.4 times Nb, which is 42.3 kilonewtons. So the answer we get is 16.9 kilonewtons. This is your friction force at point B. This is the friction force between the wheels at point B and the ground surface. Okay, so this was step 3. Now let's go to step 4. Now we have found out all the unknowns, everything. So now we need to find whether the car moves or not. Okay. So for that, let's find out the total friction force. Let's say F total is equal to Fa plus Fb. Okay, so which is 6.6 plus 16.9, we get 23.5 kilonewtons. 3.5. Okay. Now, if you look at the diagram, the free body diagram, so Fa plus Fb is 23.9, 23.5 kilonewtons, right? And the applied force in the negative x direction, the force P is 10 kilonewtons, right? So the applied force is less than the friction force. And that's why the car doesn't move, right? Because the applied force is less than the total friction force. So we can just write down that as F total greater than the applied force P, so the car doesn't move. Okay. So that's how we are done with this problem. And as you can see, just a quick review of this problem. We had this mine car with some weight, some applied force, and the wheels resting on the ground surface. So first we need to make a free body diagram showing all the forces, the external forces, the weight, the normal forces, and the friction forces. So once we are done with the free body diagram, then we need to apply equations of equilibrium, right? So once we apply the equations of equilibrium, we can find the unknowns. In this case, we have 4 unknowns: Fa, Fb, Na, and Nb, 2 normal forces and 2 friction forces. Okay, so by applying to the moment equation at point B and summation of forces in y direction, and then 2 friction equations, we could find out all of these 4 unknowns, right? So the first part of the problem is done. The second part of the problem was to find out whether the car moves or not. So in that case, we need to find the total friction force. So total friction force is Fa plus Fb, which comes out to 23.5 kilonewtons. Okay, so the applied force is 10 kilonewtons and the friction force is 23.5 kilonewtons. The applied force is less than the friction force. That's why we would say that the car doesn't move or car remains static, right? We need more force, or we need to increase the force P, the applied force P, in order to move the car. Okay. All right. So with this, we are done with problem 1 of your handout. Now let's go to problem 2 of your handout. Let's see, what do we have? Okay. So if you go through the statement of this problem 2, what do you have? The spool of wire having a weight of 300 pounds rests on the ground at point B and against the wall at point A. Determine the force P required to begin pulling the wire horizontally off the spool. The coefficient of static friction between the spool and its points of contact is 0.25. Okay, so there's a spool of wire resting at 2 points A and B at the floor and against the wall, and there's a force P which is applied to that wire, and we want to find out this force P, right? So to pull the wire. Okay, so again, first thing is draw a free body diagram, because without a free body diagram we cannot analyze the system, right? So draw the free body diagram. Now let's draw a free body diagram. So this is the ground surface and the wall. Now if I can draw this spool correctly, let's assume that this is a spool. This is the center, this point O. And this is the wire which we are pulling with force P. Okay. Now this is the outline sketch of the system. So now let's draw the forces which are acting. Okay. So first we have the weight of the spool acting at point O. So which is, you know, the value, it's 300 pounds. Right. Now let's say this is point B, this is point A, this point and this point. Okay, so now at this point B, we have a normal force, let's say N sub B. Now this spool or this force is acting in positive X direction, right? So the FB will be acting opposite to that direction. So this is your FB. Now at point A, again, this is your normal force, which is normal to the surface. So this is your N sub A. Now again, at point A, the spool is moving in positive Y direction, right? So the friction force will be in negative Y direction. So this is your F sub A. Okay, there are some dimensions which are given. Let's draw them. So this guy is 3 feet and this guy is 1 feet. Okay, so with this we are done with the free body diagram. Now let's see how many unknowns do we have in this free body diagram. NA, NB, FA, FB, and P. So we have 5 unknowns, right? So let's say we have 5 unknowns. What does that mean? That means that we need 5 equations, right? So let's say we have 3 equations of equilibrium and 2 friction equations, right? So that's how we can make out 5 equations to solve for these 5 unknowns, right? Okay, so we have 5 unknowns, so we need 5 equations. So now step 2, we can apply equations of equilibrium. Okay, now let's apply equations of equilibrium. First of all, let's apply rightward positive summation of forces in x direction equals to 0. If you do that, we have this force P acting in positive x direction, and we have n sub A acting in negative x direction, then we have F sub B acting again in negative x direction equals to 0. So we have these three forces acting in x direction. All of these are unknown, so let's call it equation 1. Okay. Next, let's do summation of forces in y directions equals to 0. Let's do that. How many forces in y direction? We have n sub b, we have negative F sub A, and we have a negative 300, which is the weight of this spool, equal to 0. Again, NB and FA are unknown, so let's call it equation 2. Okay. Third equation of equilibrium, let's take summation of moments at point O equals to 0. Point O is the center point of the spool. Okay. So if you do that, what we get P times 1. 1 is the momentum. Negative FB times 3 is the momentum. Negative FA times 3, which is the momentum, equals to 0. So 3 moments are acting at point O, right? And A doesn't give any moment because it's passing through point O, and NB also doesn't have any moment because it is also passing through point O. So only the P, the applied force, the FB and FA are giving the moment at point O. W is also not giving moment at point O because this is also passing through point O. Okay, so if you just simplify a little bit, we get P minus 3FB minus 3FA equals to 0. Let's call it equation 3 because, again, these are unknown. Okay, so we got 3 equations, 1, 2, and 3. Now, step 3, we can apply the friction equations. Apply the friction equations. Let's see. So at point A, F sub A equals mu times NA. Right? Mu is 0.25. So you get 0.25 times N sub A. Okay. So this is your equation 4. Now at point B, FB equals mu times NB, which is 0.25 N sub B. This is your equation 5. Okay, so now we have these 5 equations, 1, 2, 3, 4, and 5. So we can use any method to solve these 5 equations to solve for these 5 unknowns, right? Because we had these 5 unknowns in our system, in our free body diagram, and we applied equations of equilibrium and equations of friction, and we come up with these 5 equations, right? So now we can solve these equations in any way, by any method, whichever you like, and we can solve for these 5 unknowns, right? Okay, so how I tackle this problem, let's say step 4, solving 5 equations. Again, you can solve these equations by any method you like. Okay, so how I do it, on equation 4, I get N sub A equals 4 times FA. Right? from equation 5, we get n sub b equals 4 times fb. Okay. Now, what value of NA in equation 1? Do that, P minus 4 times FA minus FB equals to 0. Now, if you use equation 3 here, which is P minus 3FB minus 3FA equals to 0. Now you have these three equations, and if you subtract this equation, these two equations, so this is gone, and you get minus FA plus 2FB equals to 0. Right? Let's call it equation 6. Now use equation 2, which is NB minus FA minus 300 equals to 0. Right? Now here, put NB equals 4FB. So you get 4FB minus FA equals 300. Let's call it equation 7. Right? So now, if you solve equations 6 and 7, you have minus FA plus 2FB equals to 0. And you have 4FB minus FA equals 300. Just subtract these. What do you get? You get minus 2FB equals minus 300. And from here, you get FB equals 150 pounds. After you are done with one unknown, then rest is easy. Just put in the values in the equations, and you can find out the rest of the unknowns. Okay, so FB equals 150 pounds. You get FA, it will be 300 pounds. NA will be 1200 pounds. N sub B equals 600 pounds. And P is 1350 pounds, 1350 pounds. So that's how you're done with these 5 unknowns. This was my method of solving these 5 equations, but you can solve these 5 equations by any method of your choice, and till the time you come up with this answer, force P equals 1350 pounds, we are good with any method. Okay, so that's how we solved this problem. You just go back. So this was the spool which was resting at point A at the ground and against the wall at point A, right? And there was a force applied to the wire, the force P acting in the positive x direction, and we were required to find this force P when to pull this wire. Okay, so we first did the free body diagram. And in order to draw the free body diagram, we know that there are normal forces, there are friction forces at the point of contacts, right? Then there's a weight of that spool acting at point O downwards, right? And then there's a force P. So in total, we had 5 unknowns, so we were required to, we were needing 5 equations, right? So we had 3 equations of equilibrium, we had 2 equations of friction. So in total, we had 5 equations, and we made these 5 equations in this manner, and then we were to solve these 5 equations for these 5 unknowns. So you can use any method to solve these equations. I used this method, which I explained earlier, and finally we were able to find out these 5 unknowns. Okay, so with that we come to the end of problem 2. Now let's do problem 3 of your handout. Let's talk about problem 3. What is the statement of the problem 3 of your handout? Let's go through the statement. The spool of wire having a weight of 300 pounds rests on the ground at B and against the wall at A. Okay, so a similar problem, similar to problem 2, determine the normal force acting on the spool at point A if P equals 300 pounds. So in this problem, we are given the applied force, right, 300 pounds. The coefficient of static friction between the spool and the ground at B is mu s is 0.35. The wall at A is smooth, right? So what we need to find the normal force at point A. So N sub A. Okay, so this is the problem. Now, the main thing to note here is the last sentence of this statement. The wall at A is smooth. Okay, so you need to make sure that you understand the meaning of this statement, right? Because once we have a smooth contact between two surfaces, between two materials, it means that there's no friction. So we don't have friction at point A, right? So it's not true in the real world, but in problem solving, sometimes we have such kind of statement, and we need to remember that how or what condition do we apply if there's a smooth contact, right? Okay, so let's come back to this problem and let's start with the free body diagram again. So draw the free body diagram of this problem. Okay, so this is the wall, this is the floor. Okay, let's use some other color to draw the spool. Let's say this is a spool. This is the center of the spool, and this is the wire where the force P is applied, which is 300 pounds. Okay, this is point A, this is point B. Okay, and this is 1 feet, this is 3 feet. Okay, so we are done with the sketch, outline sketch. Now we need to apply the forces, right? So we already know that this is the force P, 300 pounds. So resting here, so we have a normal force, let's say N sub B, and we have a friction force, negative X direction, F sub B. Now, let's talk about point A. So it's resting here against the wall. So there is a normal force N sub A, but there's no friction force, right? So we need to make sure again that we remember this. Then we have the weight of the spool, which is 300 pounds. Okay. So that's all we have, right? And we can also write down something about point A, that the contact between the wall and spool point A is smooth. So no friction, or F sub A equals to 0. We don't need to show FA, right? Okay, so we are done with the free body diagram. We made use of that statement, the smooth contact. Now, next thing is apply equations of equilibrium. Okay. So how many unknowns do we have? We have n sub A, n sub B, and f sub B. Right? So only 3 unknowns. So not a problem. We only need 3 equations. Okay. So let's do counterclockwise positive. Summation of moments at point B equals to 0. If you do that, what do you get? N sub A times 3 is the moment arm, negative 300 clockwise moment times 2 is the moment arm equals to 0, right? Okay. From here we get N sub A equals 200 pounds. We are done with one unknown. Next, let's go for summation of moments at point O equals to 0. If you do that, you get 300 times 1 minus FB times 3 equals to 0. So only 2 forces creating moment at point O. From here, we get FB 100 pounds. Okay. Now we can apply third equation. Let's say we apply summation of forces in y direction equals to 0. Okay, if we do that, we only have NB and 300 pound force, which is the weight, equal to 0. From here, we get NB equals 300 pounds. Okay, so that's the normal force at point B, normal force at point A, and we were required to find the normal force acting on the spool at point A, right? So we already found that. Okay, so that's how this problem is done. And now let's go for step 3. If we were required to find, although it's not given in the statement, but if we require to find that if the spool will remain at rest or it will move, right? Let's do that. So let's say, what is FB max? Maximum friction force, right? So it's mu s times NB, which is 0.35 is the friction coefficient times 300, which is N sub B, right? So this guy, N sub B, this guy, times a friction coefficient. So this is 105 pounds. Right? Now we can say that since FB, which was 100 pounds, is less than FB max, so there is no slipping. If there is no slipping, then the spool will remain at rest. Okay, so that's how we are done with this problem. So we have done 3 problems on this first topic of dry friction, right, involving the friction forces and the normal forces, and to find out the unknowns using the equations of equilibrium and the friction equation, right? Okay, so that's it for this lecture, and we'll see you in the next lecture. Thank you.